let's now look at some examples of things that are homeomorphic. So lots of stuff is homeomorphic, and we'll learn more and more techniques to show they are. In fact, as long as you study topology, you'll get more and more techniques. But let's look at our first few. First, 0, 1. So remember, homeomorphism is transitive. So once we show some things, we get more for free. So 0, 1 is homeomorphic to an open interval AB if A is less than B. And the proof is we just construct the obvious map from 0, 1 to AB. And f of t is going to be A plus t into B minus A. So this is a homeomorphism. Simple analysis to check that it's continuous, and its inverse is continuous. In fact, there you can write the explicit formula. So corollary here is that any two open intervals are homeomorphic. Now exactly the same way we get any two closed intervals. Are homeomorphic. And what about half open intervals? Well, it doesn't matter which side they're half open, any two half open intervals, as long as they're both exactly half open, are homeomorphic. Well, by transitivity, we just have to show. So I'll just call it a remark. It's only a small piece of the proof. So homeomorphism f from, we have, let's say it's half open this way, and we have the other way. Well, that's clear, right? So given by f of, we just want to flip. So f of t equals 1 minus t is a homeomorphism. So we reflect, we'll get a homeomorphism from these. Okay, these are not surprising. They just tell you can change the scale. Okay. Slightly more interesting one, which will distort the shape a little bit, is let's take, draw it with straight lines. Let's take a square, unit square. So this, and let's take a parallelogram. Okay, my thing is not quite parallel, but it's supposed to be a parallelogram. So to draw this slightly better. So let's give them names now. So this is x, this is 0, 1 cross 0, 1. And this is y, which is a parallelogram. I'll call this point P. I'll call this vector u and this vector v, and we'll use vectors. So then f from x to y, we'll write the formula. F of a point s and t is going to be the vector p. So this is a vector p, and then you have u and v are vectors p plus s times the vector u plus t times the vector v. This is a homeomorphism. So in fact, affine transformations which are invertible, which are automatically invertible, are also homeomorphisms. Okay, so it doesn't look like a parallelogram, but if it is, that would be homeomorphic. Actually, this quadrilateral will also be homeomorphic, as we will see soon. Okay, so here are some examples. Another example, and then we'll see a few which are slightly more complicated. And as I said, including all polygons. At least all convex polygons, we'll see a procedure that works, and then this actually works for any polygon. Okay, with some modifications. So let's take here's an example where also these were all finite objects. Okay, so 0, 1 is homeomorphic. So an open interval, but not a closed interval, is homeomorphic to R. Well, first let's just take half R, 0, infinity. Well, using what is the function f of t, I want to send 0, 1 to 0, infinity. If I look at log of a number between 0 and 1, it ends up between, it's negative. So if I take minus log of that, and t, as t goes to 0, this goes to infinity. Okay. So this is, of course, depends on special functions. We'll see in the next segment, next lecture, when we are looking at pasting, how to do this in a more sort of topological way without using special functions. Now similarly, 0, 1 is homeomorphic to R. This time we will take a function from 0, 1, so using appropriate trigonometric functions, so using tan inverse. So tan inverse shoots off to plus infinity and minus infinity when you're within a particular range. This needs a bit of rescaling, but now we want to look at a little larger class of examples. So these showed that homeomorphism doesn't respect being bounded, for example, so that is important. It can distort shapes, but it can do more, and we'll look at a more general procedure. But for the general procedure, we'll first look at something more concrete. So let's take, suppose this is the origin 0, 0, and let's take a circle centered at the origin. Okay, that wasn't quite the center. And let's take a rectangle that contains the circle. And I claim that the interiors of both of these, well, let's improve the center. That circle actually became an ellipse, but we'll ignore that fact. And we see this point 0, 0. Okay, so this is the example. I won't continue the numbering. We'll have a number. So we look at first, so the region, the disk, the inside of this D is xy such that x squared plus y squared is less than or equal to 1 is homeomorphic to minus 1, 1 cross minus 1, 1. But we'll view this in a different way. It's the set of all xy in r squared, of course, such that maximum of mod x and mod y is less than or equal to 1. And the boundary is exactly where the maximum equals 1. Because this formula will be useful. We've also done this deliberately because this becomes the unit ball in the L infinity norm. So that's why we wanted to do this. In the L1 norm, you get a diamond, which is also homeomorphic to these two. So what is the way in which we can do it? We can scale. Okay, let's map the sphere to this. Okay, so you define it. So here we'll make it explicit, and then we'll have a similar picture, more general picture, where we will not make things explicit. So let's define this. Define f from, let's call this a b or c or something like that, or a cube d to c by, well, if I took the point xy, now if it was actually on the circle, then I want to map it onto a squared. And what we do is we'll simply map in the same direction. Okay, so we'll map out radially in such a way that the point which is exactly on the boundary goes to the boundary in the same direction, and if you're in the interior, you scale accordingly. Okay, so if you were on the boundary, then what you would get is you want something on the boundary of that. So that is xy by max of mod x mod y. So if xy was not 0, this would be exactly the corresponding point on the square. But we don't want this because we want to scale according to how far we are along the disk. So this is exactly the formula you'll see. If I look at root of x squared plus y squared, this is less than or equal to 1, and it goes from 0 to 1, and this gets goes from these are points in the square, and if you wish, you can just write the inverse with inverse g of xy. Well, here the situation is the opposite. We want to normalize. If we were sending it to the circle, we'll divide it by x squared plus y squared. But in general, we are looking at a point in the square, and if it's not on the boundary, we want to go only part of the way to the boundary here. So that is max of mod x mod y. Okay, so these two you can explicitly check are inverses of each other. So both these when xy is not 0, 0. And f of 0, 0 is 0, 0, and similarly for g's. So what we can do is scale up, and this scaling up will work for any polygon, any convex, or even what is called a star convex polygon. Is homeomorphic. Well, if I said polygon, I mean its boundary to a circle and its interior to a disk. Okay, so, and including its interior to a disk. Let me just draw a polygon. So here is our polygon, which is a hexagon in this case, which I might as well draw with lines to make a little less ugly than usual. And inside it, let's put a circle of a different color. A little more in the center. It's not important that it's exactly in the center. So now I'll draw in pictures. So what is the homeomorphism? Let's take the central point of the circle, which is going to be this red point. And then if I'm given any point, blue won't stand out. Let us say an orange point on the boundary of the circle. Here the red and orange look a bit too similar, but still, and we'll take this light blue color, and we'll take a line starting at the origin, go along this and see where it hits, and the orange point maps to the orange point on the circle corresponding to that. And as you see, this is a homeomorphism. So given a polygon, whatever your favorite definition of polygon is, you take a small enough disk, and small disks are homeomorphic to big disks. So any disk will do. So we just have to find a homeomorphism to one disk. So we take a small enough disk, its boundary goes to the boundary of the polygon, and then use the same scaling trick. That is, if I have a point that is yellow is barely visible, so you have a barely visible point here along the way, then I send it to the same distance. I scale accordingly. That is, I take the proportion of the distance to the boundary this is, and take the same proportion of the distance to the other boundary, what we did with explicit formulas earlier. Okay, so its interior is to a disk. So this is a proof. Well, I've just given you a picture. So these two interiors are homeomorphic. That is, the solid polygon is a disk, and so is the circle. This used convexity, but so that's why I should say what one means by star convex. Actually, all these things need less. In fact, you need much less. You need not even be star convex, but that will take a little more work, in particular gluing that we'll see later. So let's take a non-convex polygon like this one. Okay. What I mean by star convex is if I take a red, I can find a point here, so that any given point on the boundary is connected to this by a unique line. So it's a star-like region. So this is called star convexity. Convexity means if I take any line segment joining two boundary points, they're entirely inside. That is not true here, and so this one is not true. But star convex, you just need that if I have a central point here, your star convex about this point, just the line segment joining this interior point to these, all these is contained inside the region. So if you are star convex, the same trick works. Yeah, and so you take any polygon, you can always find a point with respect to which it is star convex, and so we get more examples of homeomorphisms. So this has given a kind of rich class of examples of homeomorphisms. We'll look in the next lecture, not straight away, at powerful way of defining continuous functions, which is just a formalization of what we do always, which is defining functions in pieces. Okay, but we need it clean way in topology. But before that, so that will let us generalize many constructions. But before that, in the next lecture, we'll take another view at these, which does not involve log and tan inverse, but instead we'll define things piecewise using an order, because order topologies are also important. So